Welcome to the deep dive. We're diving into the world of quantum physics today. You send us this interview with physicist Sean Carroll talking about his book, Quanta and Fields. We figured we'd unpack some of the good stuff for you.
Yeah, we've got a lot to cover. He really gets into it, everything from basic quantum mechanics all the way to the many worlds interpretation. We'll break it down though, make sure it all makes sense.
Okay, cool. So one of the first things that jumps out is how Carroll talks about this wave function thing.
Right.
It's not just some math trick. He's saying it's like the actual reality in quantum mechanics. Way different than just thinking about positions and momentum like we do in classical physics.
Oh, yeah, totally different. It's a huge shift. Like in classical physics, we want to know where stuff is and how it's moving. Quantum mechanics, it's all about the wave function. That's how we describe the state of a quantum system, and it leads to some pretty weird stuff.
Weird how? Like, what even is a particle if this wave function is running the show?
Well, that's the thing. Particles, they're not really like little solid things the way we usually picture them. They're more like ripples in an underlying field.
Ripples.
Yeah, think about like a guitar string. You pluck it, it vibrates, that's what makes the sound. Particles are kind of like that. They're these quantized excitations of these underlying fields.
So instead of picturing an electron like a tiny little ball, it's more like a wave in this electron field.
Exactly. And that actually explains why all electrons are the same, why they're identical, because they're all just like vibrations of the same field.
Huh, that's pretty neat. But then there's this measurement problem thing.
Yeah.
That always kind of messes with my head.
Yeah, the measurement problem. It's definitely a puzzle. It's basically like when you try to measure a quantum system, it goes from being in all these states at once, superposition, right?
Yeah.
And it collapses into just one specific state. It's like reality suddenly decides what it wants to be when we look at it.
It's like the Schrodinger's cat thing. The cat's both alive and dead until you open the box, right?
Exactly. And the weird part is we still don't really know what counts as a measurement or what makes the wave function collapse. It's a big mystery.
So just observing something can, like, change reality at the quantum level.
Right.
That's kind of freaky.
Right. And then you add entanglement on top of that.
Yeah.
It gets even weirder.
Ah, entanglement. That's spooky action at a distance, right?
Yeah.
Even Einstein had a problem with that one.
He did. And it really shows you how different the quantum world is. Things aren't all neat and separate like in classical physics. When particles are entangled, their fates are linked. It doesn't matter how far apart they are. You measure one, the other one's affected instantly.
It's like they're connected by some invisible string or something, even across, like, galaxies.
And some physicists think that this entanglement thing, this connection with the environment, could be the key to figuring out the measurement problem. Like when you measure something, you're interacting with the environment, and maybe that's what forces the wave function to collapse.
So the environment isn't just sitting there. It's like part of the action.
Maybe. It's an active participant in shaping quantum reality. It's pretty cool to think about. Now, Carroll also talks about quantum field theory, or QFT. He says it's the best description of the universe we have so far.
QFT, yeah. I've heard of it, but it always sounded super complicated. Like, can you even understand it without a PhD?
Well, it can get complex, but Carroll does a good job breaking it down. The big idea is that it brings together particles and fields. He shows how particles are really just like excitations of these fields.
So like the electron field we were talking about before, that's what QFT is all about.
Yeah, QFT gives us a way to understand all the fundamental particles and forces as part of these fields.
Huh. So it's like a unified picture of everything.
Huh?
Pretty cool. He also mentions these Feynman diagrams. Those little diagrams physicists use with all the squiggly lines. Are those just like visual aids, or is there more to them?
Oh no, they're way more than just doodles. Feynman diagrams are a really powerful tool. They let physicists calculate probabilities in QFT.
Probabilities of what?
Probabilities of like how particles interact, how they exchange other particles like photons.
So they're like a shorthand for describing what's going on in the quantum world.
Exactly. But here's the thing. Sometimes those calculations can lead to infinities, which obviously doesn't make sense in the real world.
Infinities?
Yes.
That doesn't sound good. How do they deal with that?
Well, that's where effective field theory comes in, or EFT. It's basically saying we don't know everything about physics at super high energies. So instead of getting stuck on those infinities, EFT lets us focus on the energy scales that are relevant for the problem we're working on. We can kind of ignore the infinities that way.
It's like zooming in on the parts we can understand and ignoring the really high energy stuff that we can't handle yet.
Yeah, exactly. It's a practical approach, and it's worked really well, but there are still big mysteries, like the hierarchy problem. Carroll talks about that.
A hierarchy problem, what's that?
It's basically this puzzle about why gravity is so much weaker than the other fundamental forces.
Huh. Gravity's weak. I wouldn't want to fall off a building and test that theory.
Well, it's all relative, but yeah, gravity operates at this incredibly high energy scale, the Planck scale, and the other forces are way, way lower on the energy scale, so there's this massive gap.
So we've got this huge difference in the strength of the forces. Why is that?
That's the problem. We don't really know. EFT doesn't explain why, but it lets us work with it.
So it's like saying, okay, we don't know why this is happening, but we can still do physics.
Yeah, exactly. And then there's another head scratcher, the cosmological constant problem. This one's even weirder, I think.
All right, lay it on me. What's the cosmological constant problem?
It's basically this huge mismatch between what our theories predict for the energy of empty space and what we actually observe.
Wait, empty space has energy.
According to quantum field theory, yes. But the amount of energy we see is ridiculously smaller than what the theory says it should be.
So our best theory about the universe is, like, way off.
That's the problem. This huge difference tells us something's missing in our understanding. Like, maybe QFT is right, but it needs some tweaking. Or maybe we need a totally new approach.
Whoa, that's a lot to think about.
It is. It's kind of unsettling, but also really exciting. It means there's still so much we don't know about the universe.
Yeah, definitely. So we've talked about wave functions, particles being like vibrations in fields, entanglement, Feynman diagrams, and now the hierarchy problem and the cosmological constant problem. My brain's starting to hurt.
I know, it's a lot. We've covered a lot of ground. But we're just getting started. In the next part, we're going to dive into even weirder stuff, like the many worlds interpretation and what all this means for how we understand reality.
Okay, I think I need a break before we go there. But before we jump to part two, what's something that's really stood out to you so far?
Honestly, it's how quantum physics just completely changes how we think about the world. Like the idea of particles being more like vibrations in a field, it's mind-blowing.
Yeah, for me, it's the entanglement thing. Two particles being connected like that across huge distances. It makes you wonder about what space and time even are.
Right. It definitely raises more questions than it answers, but that's what makes this stuff so fascinating, right?
Totally. Well, we'll wrap up part one here, but stick around for part two, where we'll keep exploring the amazing world of quantum physics.
Welcome back. We're continuing our deep dive into quantum physics with Sean Carroll. Last time, we got into the basics of quantum mechanics, things like the wave function, entanglement, and quantum field theory. Now, things are about to get even weirder.
Okay, I'm ready to get weird. So let's talk about this many worlds interpretation. That's the one where every time there's a quantum measurement, like the universe splits, right?
Yeah, that's it. It takes superposition to the extreme. Instead of one universe with a definite history, we get a multiverse. Every possible outcome of every measurement, it gets its own universe.
So Schrodinger's cat isn't alive or dead. There's one universe where it's alive and another where it's dead. And these universes keep branching off with every measurement.
That's the basic idea, like a choose-your-own-adventure book, but every choice makes a new reality.
Whoa, that's a lot to take in. Okay, but even if we go with that, how do we deal with the number of universes? It's like infinity, right? It's got to be overwhelming.
It's definitely a lot. Carroll's point is, don't get hung up on the infinity of it all. Focus on the probabilities. Some branches of the multiverse are more likely than others.
So it's like, okay, there might be infinite possibilities, but let's just worry about the ones that are most likely to, look like ours.
Exactly. Makes it a little easier to think about.
Makes sense. But if the universe keeps splitting, why don't we experience it? Why do we only see our reality?
Good question. The idea is the different universes split off so fast they don't interact anymore. Each branch is isolated, it does its own thing.
So we're trapped in our little bubble, unaware of all these other versions of ourselves, living out other possibilities.
Pretty much. It's not like you can hop between universes, even though it'd be cool.
Oh, man. I was hoping for some multiverse travel.
Maybe in another branch you are.
Okay, that thought is both amazing and terrifying at the same time. But let's stick with this branch for now and talk about fine-tuning. Carroll mentioned that word gets used in different ways, right?
Yeah. One way is about the conditions for life to exist. Like the right kind of planet, the right values for fundamental constants, fine-tuning for life, they call it. The other way is about our theories themselves. Some parameters have to be just right for the theories to work.
So on one hand, it's saying the universe is set up for life. But then there's also this idea that our theories need to be fine-tuned to make sense of the universe.
Exactly. And Carroll says don't jump to conclusions, especially about life. We're still figuring things out. Maybe there are explanations we haven't found yet.
Like finding a perfectly tuned piano in the woods. You might assume someone tuned it, but maybe there's another reason.
Great analogy. We got to keep an open mind. Okay, so getting down to basics here. What really exists at the most fundamental level? What does Carroll say? He thinks it might just be the quantum wave function itself, the one from the Schrödinger equation. But the thing is, we usually think of wave functions of something, a particle, a field. But maybe in the quantum world, the wave function is the fundamental reality, not a wave function of anything.
So it's not describing something, it is the something. Whoa.
Yeah, it's a different way of thinking about it. The wave function is reality itself.
Mind blown. All right, while we're getting all philosophical, what about that big question? Why is there something instead of nothing?
That's the one, isn't it? Carroll says maybe the universe just is. A brute fact. No deeper
The
explanation.
universe exists because it exists. No ultimate why.
Maybe not. Maybe that's just how reality is. It's humbling, but it shows us the limits of what we know. Some questions might be beyond our reach, at least for now.
Yeah, a lot to ponder. It seems the more we dig into quantum physics, the more we have to face the mysteries of the universe and the limits of how we understand things.
It's a journey, that's for sure. But we're only scratching the surface here. There's so much more to discover in the quantum world.
Okay, before we go to part 3, what's one thing that's really challenged how you see the world?
For me, it's this idea that space and time might not be as fundamental as we thought. If they really emerge from entanglement, well, that changes everything.
I'm with you there. It's like the ground is shifting under our feet and we're trying to find our footing in this new quantum landscape.
Exactly. It's disorienting, but it's also exciting. A whole new way of seeing the universe is waiting for us to discover it.
All right, we're back for the final part of our quantum physics deep dive with Sean Carroll. We've gone pretty deep already, talking about the wave function being reality, all these splitting universes. Now let's get even more speculative, see where these ideas take us.
Yeah, we've covered some crazy stuff. But quantum physics really makes you think about the big questions. Like, what are space and time, really?
Okay, yeah. In classical physics, they seem pretty straightforward, but something tells me it's not that simple in the quantum world.
You got that right. Time, especially. In classical physics, it's this absolute thing ticking away for everyone the same. But quantum physics, it kind of throws a wrench in that.
I've heard some wild theories about time. Like, it's an illusion, or it comes from something else, something deeper. Is there anything to that?
Some physicists actually think so. One idea is that time comes from entanglement. Remember that connection between particles. While some theories say as particles get entangled, they create a kind of time connection too, like they're building the fabric of time itself.
So time isn't this background thing, this stage for the universe. It's being created all the time through these quantum interactions.
That's one way to think about it. It's pretty different from how we usually think about time, but it's a real possibility some physicists are exploring.
Wow, my mind is bending. And space.
Mhm.
Does quantum physics mess with that too?
Oh, yeah. Actually, there's an idea about space that's connected to time emerging from entanglement. Some physicists think maybe space itself also comes from entanglement.
Wait, really? So space isn't this big empty box that holds everything? It's more like a web of connections made by
Uh-huh.
entanglement.
Exactly. It fits with this idea that quantum connections are more fundamental than the space and time we experience in our everyday lives.
It makes you wonder what we think of as the physical world. Maybe it's just the surface. Underneath, there's this quantum reality where everything's connected in ways we don't even get yet.
That's a really deep point, and it leads to even bigger questions. If space and time aren't fundamental, what is? What's the foundation of everything?
Well, we've talked about the wave function as this maybe fundamental thing. Could it be that the wave function is the base reality?
That's what physicists and philosophers are trying to figure out. If the wave function is reality and space and time come from entanglement, well, the universe looks a lot different than we thought.
It's a universe where the observer and the observed, they're not so separate anymore. And reality is always changing, woven together by these quantum connections. It's amazing and kind of scary too.
I agree. It's a universe that's telling us to let go of our old ways of thinking. We got to embrace the weirdness, the uncertainty, and the connections in the quantum world.
This deep dive has been amazing. It's really changed how I see the world. I used to think physics was about finding the tiniest pieces of stuff and the rules for how they work. Now I see it's way bigger than that. It's about understanding what reality is, even if it takes us to the limits of what we can understand.
That's a great way to put it. Physics isn't just about equations and experiments. It's about asking the biggest questions we can think of. What's the universe made of? How does it work? What does it mean to exist?
And exploring Sean Carroll's ideas has shown us that those questions can lead to some mind-blowing places. We've encountered superposition, entanglement, all these multiple universes, the idea that even space and time might not be what they seem.
It's a wild ride for sure, but it makes you realize how much we don't know, how much is still hidden beneath the surface of reality.
Yeah, it's humbling. Well, I think we've reached the end of our quantum journey for now, but it feels like just the beginning, right? There's so much more out there to explore.
Totally. We might not have all the answers, but the journey is what makes it so great. It's about pushing the limits of what we know, being okay with not knowing, and always being curious about the nature of reality.
You've been an awesome guide through all these ideas. I've learned a ton, and I'm definitely leaving with more questions than answers, but I think that's a good thing.
Absolutely. The best questions are the ones that keep us looking for answers, keep us wondering, keep us exploring.
Well, to everyone listening, thanks for coming along with us on this quantum deep dive. Keep asking questions, keep exploring, and keep wondering. Until next time.